Hello and welcome to today's episode of the Exposure Scientist podcast. Today, we're going to be discussing an interesting topic, a topic that we've discussed previously, PFAS, but from a different way of looking at PFAS, back from the toxicological side, but more so from the environmental side. So today we're going to be talking about PFAS source tracking using analytical fingerprinting. That's an interesting topic, and to introduce that topic and discuss it, I brought somebody who's an expert in that field, Dr. Ioana Petrisor. She is a chief chemist at NSAFE. Ioana, thank you very much for joining us today.
You're very welcome. My pleasure.
Please tell us a little bit about yourself.
Yes, well, so hello everyone. I am a biochemist, and as anyone can notice, I am talking with an accent. And this is because I am originally from Romania, which is in Eastern Europe. So I was born and educated in Romania as a biochemist. And I have been in the United States since the beginning of 2001. I have been a postdoctoral fellow at Florida State University, then at University of Southern California in Los Angeles. After that, in 2003, I started my first consulting job, and that was with an environmental consulting company that basically my assignment with that company was to conduct forensics investigations. And that's really very exciting for me. It's like conducting CSI type of investigations, but that relates to the environmental pollution, which is also can be seen as a crime. And as compared to criminal, investigations and criminal crime, environmental crime can be more outstanding because it can impact more people. And if the groundwater or the water, the drinking water source is contaminated, tens of thousands, hundreds of thousands, millions of people may be impacted. And many times the impact is not immediate, but with a lifetime exposure, people start developing cancers. They may have other chronic issues in later years. And certainly environmental pollution may, contribute to this. And so my first consulting job was conduct for environmental forensic studies, which means evaluating the source and the age of environmental contaminants. And with that job, I changed several jobs. I work for different companies along the years, but I kept doing this environmental CSI type of studies. And I'm very proud of this. I enjoy doing it. More recently, I am focused on these emerging contaminants that we refer to as PFAS, per and polyfluorinated alkyl substances.
And I appreciate that. And I wanted your expertise here to discuss those PFAS substances. We hear it all the time. There's lots of news articles. I don't think a day goes by where I don't see a news article discussing PFAS in some form or fashion, from either a contamination problem or a groundwater problem or drinking water issue. So if you could explain to the listeners, can you define PFAS for us? Can you provide their characteristics to this? And I know this is going to be in a general term because as your listeners, you'll find out there are lots of PFAS. So if you could kind of give us a broad overview, that would be very helpful.
Yes, of course. It is very hard to clearly define PFAS, and this is one issue related to PFAS. Well, we have a name for them, and I just mentioned it. The abbreviation is PFAS, and this is a class of chemicals. So there are multiple chemicals that basically all of them have something in common. They have carbon and fluorine in their structure. Because they have carbon, because they are carbon-based, these are organic chemicals. However, there are many definitions out there related to what constitute a PFAS that go into the detail of their structure. So some definitions would exclude compounds with double links, for example, in the carbon chain. Some definitions maybe will include one or more fully fluorinated carbon atoms, which means all the valencies of the carbons are filled by fluorine. So we have just carbon and fluorine, and also a terminal group. So no hydrogen. And the most inclusive definition that, as far as I know, it has not been adopted by any governmental agency and may never be adopted, but the most inclusive one would be that any organic compound that has carbon and fluorine in their formula and in their structure would be a PFAS. And that would mean potentially millions of chemicals out there. But even if we refer to some more restrictive definitions that would include fully fluorinated carbon atom, then we would still end up with at least 10,000 of these individual chemicals. And you notice that in the name there are two types of chemicals. We said per and poly. And that refers to to a carbon atom, if it is fully fluorinated or not, which means if the carbon atom is only linked to fluorine and another carbon or other carbons, it is considered that it is fully fluorinated. And those are the pair compounds or the pair PFAS. Perfluorinated PFAS, that only have fully fluorinated carbon atoms in their structure. The poly PFAS are those PFAS that have one or more carbon atoms in their structure, and they could have, 10, 12, 14, a larger number of carbon atoms, starting with one and going to many of them. But if at least one of them is not fully fluorinated, which means it's linked to fluorine, to another carbon, but may be linked to hydrogen or another atom that is not carbon or fluorine. So it is considered not fully fluorinated, and those compounds would come in the category of poly PFAS or polyfluorinated PFAS. Now, this is significant because carbon, the link between carbon and fluorine, it is the strongest chemical link that we know so far. Because of that, it is very hard to break. So the pair PFAS or the perfluorinated PFAS are extremely persistent in the environment. We need very high energy input to break that link. And this is how they are produced. Using high energy, you need high energy to break the link. So typically that's why they are called forever chemicals. Now, of course, forever chemicals, people use forever chemicals to refer to all the PFAS compounds. However, the poly PFAS, which are a large number of PFAS that are manufactured and used, are not forever. However, the link that is not carbon and fluorine will break and may break very easily in some cases. But these PFAS will end up generating perfluorinated PFAS with a smaller carbon number in their structure. So therefore, even though they are not forever, they will break, they will end up generating forever chemicals. So I think the forever chemical name is correct to refer to the whole class of PFAS.
And listeners, as Ioana just explained, there's a lot of chemicals in this class, and there's a lot of, I'll say, technical details. So when people are talking about these, where you hear the general term PFAS, there's a lot of thought process that has to go into it from a number of different standpoints when we're evaluating environmental deposition or exposure or toxicity to them. So we hear this term PFAS. People are looking for it now in drinking water. Can you provide a little bit of the history, the backstory of what PFAS has been traditionally used for, and where has it ended up from that use?
Yes. So I'll start with the end of your question because it's easier to explain. PFAS are everywhere. And when I say everywhere, I just don't mean in every environment, everywhere on the planet. It's also in all the living beings right now. as far as we know, as far as we tested. So really, to find human blood without PFAS, it's extremely rare. I don't say it's impossible, but it will be extremely rare. And typically, any blood bank coming from before the Second World War would be free of PFAS. And this is because, and now I'm going back to the beginning of your question, PFAS started being manufactured in the 40s and 50s. And basically, they were commercially available on a larger scale since 1950s. As far as I know, this is a consensus right now. And their main use, well, they have multiple uses, and we can go over those. But one use that is very well known within the environmental community and maybe within the public at large is their use in firefighting foams, or what we called AFFs, AFFF, which stands for a type of firefighting foams, which are from the Class B firefighting foams that are used to treat fires that are very hard to treat, like petroleum fires. Fires that are ignited and they have petroleum compounds as fuels. And as everybody knows, if you want to start a fire and you have some fuel oil there, you'll start it immediately than without it. So now, the reason the PFAS are used in firefighting foam and in many other uses, it's because they have some specific characteristics. On top of being forever, they have most of PFAS would have surfactant behavior. And surfactants are those compounds that are used in detergents, all sorts of soaps and detergents. Surfactants are compounds that have a hydrophobic and a hydrophilic part in their structure. And the hydrophobic segment or part would be repelling water and would be the organic, the chain of carbon atoms. And they can be linear or can be branch, but all PFAS would have carbon and fluorine, as we already discussed, and that chain of carbons linked with each other and with fluorine would constitute the hydrophobic part. The hydrophilic part of that most PFAS have are some sort of polar group, and those would be electrically charged and would be something like a carboxylic group, and that gives them acid behavior now and the acid name, like any carboxylic acid. So carboxylic could be one of these groups, and it is very important. And sulfonic group, it's another acid group that has sulfur in it. Those constitute two major classes of PFAS that we studied so far, and our regulations are focused on, which are the perfluoroalkyl carboxylic acid and perfluoroalkyl sulfonic acids. Or the so-called perfluoroalkyl acids. There are other type of acids, many others that are included as could be PFAS, but these are major ones. So the carbon chain would give them hydrophilic, would repel the water, and this carboxylic or sulfonic group or another type of polar group could be hydroxyl, could be a different type of group, would have the property of attracting or of being dissolved into water, if you like. So because of that, PFAS have a series of peculiar characteristics, including that they would accumulate at interfaces between different media like water and air, water and soil, water and oil, and so on. They also, most PFAS, I would say, have this oleophilic behavior. They really attract oil and also repel oil or organic compounds. So basically, that's a main property of PFAS, and that gives them detergent behavior, emulsifying behavior. It's also the property of repelling water, and a lot of waterproof things that we know and we have and we use every day, and including coatings for carpets and the many consumer products and this outdoor equipment, the raincoats that are resistant and they don't get wet, rain shoes and so on, waxes, they all have PFAS in them because it's really, PFAS are very useful. The Teflon coatings in the Teflon pans. And with this being said, a lot of consumer products, if not the majority of consumer products, have some PFAS in them, some PFAS compounds, because really they provide very good water repellents, oil repellents properties, temperature stability, as well as some properties that help those products last more and serve their purpose. Now we all know how useful the Teflon pan was when introduced, no, and how much you have to scratch and clean a pan if it's not Teflon or if it doesn't have a coating on it that will, repel water. I mean, we are so used to this type of pans that if we go back to the other pans, I mean, it will be a lot of work to clean them. So PFAS are the main culprits, but of course, they help us in many ways. They are very helpful in semi. For example, another example would be in computer chips and semiconductors. PFAS have a very important role, and that role it's right now it's unreplaceable. It looks to be unreplaceable. There hopefully will be replacement chemicals. But in some situations, PFAS have very essential role. In some situations, they are just a commodity, but nevertheless, they are used by many industries, and they are in many consumer products and in many products. And certainly, we found them in all the environments, even in the poles, the Arctic pole, in that ice, because they travel.
Right. No, and I think it's, to add some context from that, and, you're talking about the AFFF foam, and I think it's important to provide this to the listeners. It's, of course it's used in firefighting, but you have to think it's not the fact that there's that many fires. It's the fact that these materials were used in training of firefighters very often without understanding the full implications or ramifications of just simply washing it off into the side of the road or what have you. Is that, it's not just the limited uses of it. They were also used in training modules for firefighters all across the United States.
Absolutely. Yeah, you are absolutely right. So, of course, PFAS had important uses to treat or put off the fires, petroleum fires, and that was one way they spread in the environment. However, an important way got into our environment is just by training. And right now, I don't think anyone in the US is conducting training, active training, firefighting training using AFFFs anymore. And I know that there is an active campaign to replace the AFFF foams with non-fluorinated foams, which is really great. But in the past, fire training used AFFF and they were just going down the drain.
Yeah.
In
So,
rivers,
yeah.
environment.
I'll ask this question is, and again, in recent years, a lot of this, from what I understand, is, the firefighting, because petroleum fires, they practice at airports, they practice in areas where they're going to have a large petroleum issue. A few years ago, I say 10, 15 years ago, I think there was, FAA was kind of looking at this, Federal Aviation Administration, saying, okay, maybe we should look at the shorter chain PFAS to use in these scenarios. Have you seen anything with changing it to different PFAS for use in these scenarios and how they interact with the environment from their use and maybe in training in more recent years as opposed to training in the 70s or 80s, again, if we're talking about something that will last or persist forever?
Yes, as a matter of fact, since about 2012, I think most of the manufactured firefighting foam that had PFAS in it, like AFFF, is what is we like to refer to as modern foam, and this would be a C6 or lower foam, which means the older foam had 8 compounds with PFAS compounds with 8 carbon atoms and more, and also with lower carbon atoms. But the modern firefighting foam try to eliminate these long chain PFAS that have 8 carbon atoms, like PFOA, PFOS. Those are pretty famous PFAS that are already regulated by EPA in various ways. But they still have PFAS, these modern foams, or they generate, they have most of them would have these PFAS, poly compounds, which are not fully fluorinated compounds. But those compounds would generate PFAS, perfluorinated PFAS, with 6 carbon atoms or less. And the general idea is the shorter the chain, the less problematic the PFAS is from the point of view of persistence, of health effects, and so on. However, recent studies, studies, I guess, in the past decade or more, show us that these replacement PFAS, including replacement AFFF foams, are still problematic. And maybe we have less toxicity, but they are still toxic, and some of them may be carcinogenic to humans. And certainly all the perfluorinated PFAS are kind of forever. Now, unless we do something actively, they will persist in the environment. They will move between soil, water, air, and they will recycle, and they can move over long distances via air and ocean water and reach the poles. And basically, we found them in all the environments we look for them. So because of that, and because it's very hard to study every single PFAS. There could be tens of thousands or even more PFAS. Maybe some of them could be fine, but it is absolutely impractical and infeasible to study all of them. People try to move away from the PFAS as a class, and that's another thing that it really makes PFAS apart from other chemicals, because the tendency is to regulate or to eliminate them, to treat them as a class rather than individual compounds, and basically move away from PFAS. And any industrial company, and any company that has PFAS issues know that, and they start being very aware and try to stay away from any sort of PFAS, because even if they are not regulated today, they could be regulated tomorrow as a class or as individual PFAS. So yes, there are alternatives. There is this modern AFFF that has been used in the past decade or more, almost exclusively. However, all the legacy AFFF with long chain PFAS still exist, and still exist in many locations. It has a very long shelf life. So even if that was not manufactured starting in the beginning of 2000s, a lot of it still exists, and it is stored in various locations. When you store something, like with petroleum products, you may have spills, you may have leaks. Some of them you know, some of them you may not know. And it was still used in firefighting training for some time. It all depends. It varies. But there are situations where it could have been used, as, almost very recently, or in the past 5 years or so. So we cannot exclude the use of the legacy firefighting foam, even though it was not manufactured. And, in general, all the companies try to move away from it.
Right. So we've had, and I appreciate that, we've had this conversation about use of it in the environment from I'll say industrial type scenarios, and personal products as well, that consumer products, as you talked about. And if we're finding these chemicals, if they are persistent from use, from deposition, from industrial use, from spills or whatever, I want to kind of get into, you mentioned earlier your forensic investigative techniques or forensic investigation, finding out what techniques you use to identify these in sources, discussing, how PFAS, again, as a group, as you mentioned, may be different from other chemicals when you're doing your environmental investigation. So I'd like to be able to talk about your analytical methods you use to identify these and how you see these as use and limitations of the many types of techniques that are available.
Right. That's a very good question. So, as a forensic scientist, I have used a large variety of environmental forensic techniques. I wrote articles, editorials. I didn't mention I'm also editor of Environmental Forensics Journal. And by the way, whoever is interested from the audience can consult the journal or send something for the journal. And I also wrote a book on environmental forensics. And we have a very large variety of environmental forensic techniques that we can use to study environmental contaminants and fingerprint them in order to evaluate their source and age. Out of those techniques, there are very limited number of techniques can be applied to PFAS. For example, and I'm going to talk more about those in a moment, but for example, a lot of people may be aware of the isotopes. We have both stable and radioisotopes. And many people may be aware of carbon dating of archaeological sites now using the radioactive isotopes and or age dating in general using radioactive isotopes. And maybe less people are aware, but many environmental people are aware that when we have chlorinated solvent spills, for example, we stable isotopic testing stable carbon as opposed to radioactive carbon. Stable carbon isotope can be used in various ways to evaluate the source, get a fingerprint, to evaluate fate and transport, because that stable isotope will change in composition when a contaminant get weathered, biodegraded, and so on. This technique is not available for PFAS, unfortunately. And even though it may have potential, as far as I know, we do not have a way to handle the hydrofluoric acid that may be produced when we test via this technique, and it will really degrade the equipment. So I don't see it coming in the near future. I might be wrong. I mean, there could be all sorts of advancements. We should keep an eye. But right now, isotopes are not a technique that is applied for PFAS. So what do we have when we talk about PFAS? We have the chemical analysis. That's how we know PFAS are in environment and in human blood and in animals, because we chemically test for individual PFAS. And we have all sorts of variations of the chemical analysis I'm going to talk about right now. And there are 4 types of variations of this chemical analysis that are distinct techniques that we can use in environmental forensics, looking at PFAS sources or trying to get more details of a PFAS release. But any of these techniques could be applied outside the environmental forensics context to better understand what PFAS are released, how they were released, where are the main sources in order to eliminate and, take care of that release and make sure we clean everything that was released. So the main technique that people know, or people that are conducting environmental studies now, is the so-called chemical fingerprinting or targeted chemical analysis of PFAS. And targeted means we are looking for a number of individual PFAS compounds, and these PFAS compounds are from both perfluorinated PFAS and polyfluorinated PFAS classes. But what defines this technique is we need standards for these individual PFAS compounds. So individual PFAS compounds with known standards can be tested via this targeted chemical analysis, which is very reliable. There are a series of EPA and ASTM methods that can be used depending on the media. For example, for drinking water, there are two main methods that are used and are currently used by water utilities that are testing for PFAS under the UCMR 5 testing. And those methods are the EPA 537.1, and the other method is EPA method 533. And these methods basically look, most of the individual PFAS are common between these methods. Very few can only be done by 537.1. And 533, it's typically preferred by regulators. And this is why for the UCMR 5 testing, water utilities have to test twice using both of these methods. And the PFAS, number of PFAS, they test for a total of 29 PFAS. The number, I think, 4 PFAS, which are not included in 533, would be reported based on the 537.1 method. And for environment, for anything else than drinking water, basically any environmental media, including waste and environmental, biotissues, we can use another EPA method, which was recently basically finalized, that is EPA method 1633. And that method, it's looking at a total of 40 individual PFAS compounds. So these methods are extremely reliable, are pretty well developed and standardized, and it will give you 40 PFAS in your environmental sample. Now, once you get that information, you may only have one or two PFAS detects, but that's very good information to know that everything else maybe is not there, or it's in extremely low amounts that will be below detection limit. What you can do all sort of graphical representations with the data, and typically we use pie charts, colored pie charts, and that will not show the concentration, but will show the proportion between individual PFAS compounds. So let's say in these samples I have 10 detected PFAS, and then I see each pie chart would be a different color, would represent a different detected PFAS, and the size of the pie chart would tell me that that PFAS is more prevalent or less prevalent than the other PFAS. And in forensic, you're really very interested in this because every source may provide different type of pie charts. You can also use radial plots, you can use bar charts, all sort of other type of graphical depiction. And as well, you can use multivariate statistical analysis, which try to show common features between a large number of samples and eliminate basically the noise that may be there. How do sample group based on everything we know, all the chemical analytes that we know in a sample, how they cluster together. So that, the combination of these techniques can be used to look at this targeted analysis data. And we can compare samples with each other as well as with known or suspected sources, or a sample representative from a suspected source taken close from a release area where we know it was a AFFF release or a spill or so on.
Right.
But there are limitations of these things. I don't know, should I go over all the other techniques, or should I discuss the limitations of these techniques, of this particular technique first?
Well, go ahead. I think talk about the different techniques. Let's discuss the options and then say, this is what's available and this is where you need to employ caution when you're using this particular technique. I think that's fair.
Okay. So the main caution when we use a targeted chemical analysis, it's really, you don't have necessarily a caution. If you're doing it on a commercial lab with that use a standardized EPA method that is, well qualified, you don't have to worry about the quality of your data. Of course, the sampling, you have to take particular measures when you sample to avoid cross-contaminations and sample at right locations. But as long as that is done properly, basically it's very reliable, defensible data. However, the main limitation is that, well, you test for 40 compounds or less, depending on the method you apply. Some commercial labs expand the list of compounds to up to 80 to 100 individual PFAS. But what is 40 to 100 individual PFAS compared to 10,000? No? Or
Right.
thousands or even more PFAS compounds that could be out there and could be in your sample. No? So there is a lot of unknown. You basically target all the PFAS that are regulated, no, or may be regulated as individual PFAS, which is good. You get a lot of individual PFAS, no, 40, it's a good number. You have things to work on, but you still are missing potential other PFAS. And in some cases, those potential other PFAS, I'll just give you an example. ASTM, one of the ASTM methods, it's targeting on top of the typical perfluoroalkyl carboxylates and sulfonates that are targeted by these methods, all the EPA methods, it target a specific type of sulfonic, perfluoroalkyl sulfonic acids, which have a cyclic structure. And some of those are what we call isobars, or they have the same formula with some of the typical sulfonic acids, perfluorosulfonic acids such as PFOS, now with C8. And this is the main PFAS that was used in firefighting foam, that was used in, had many other uses, and also that is regulated. And, one of the not just the replacement, it was produced in parallel with PFOS, is a cyclic PFAS that is referred to as PFAS. It has a cycle of 6 carbons in a cycle and an ethyl group, now with 2 carbons linked to the cycle and a sulfonic tail. So basically, this is a cyclic isomer of PFOS that is not targeted by any EPA method. However, when people are using, and in some states, they use the STM method quite a lot, that cyclic PFAS is targeted. And it will be reported if it is detected. And even if it's not detected, it will be reported as non-detect. And when that analysis is carried out, that PFAS is in many environments, as probably is as well spread as PFOS, and in some cases it could be at much higher concentration than PFOS. And we certainly miss it by using the EPA methods, standard EPA methods. So that's just one example. Of course, there could be many other PFAS that potentially could be problematic for human health, could be problematic for the environment, for the ecosystem, and that we are missing. And also by missing them, we are missing important forensic information. And if a source has more of the other type of PFAS that we are not targeted, we cannot point out to that source. No, so that's the main limitation. It's a very targeted analysis, extremely reliable. It is relatively inexpensive, and at most sites you'll have that type of data. They acquire, if they study PFAS, they study via targeted analysis. So you can take advantage of maybe historical data in the past 10 years, 15 years or so, but you are limited to the number of PFAS compounds. So how can we overcome that limitation? Well, that's where the other techniques are coming. So we have 3 more techniques that try to overcome that limitation of the targeted analysis. And the first one that I want to talk about, because it's more used, it's what we refer to as TOP, or total oxidizable precursors. So now, what are precursors? The poly PFAS are precursors, and they are considered precursors because in the environment, they generate the perfluorinated PFAS, as we already discussed. Now, that is absolutely going to happen. It can happen in various speeds based on the environment, also based on that precursor PFAS, how easy it will be to break that bond, but it will happen. So we know that they will not stay as poly PFAS forever. And many of them will change pretty rapidly after a release in such a way that maybe once a release gets through soil and get to groundwater, you may find no poly PFAS at all because it's all changed. So this total oxidizable precursor is simply a targeted PFAS analysis that is done twice on your sample. Initially, as you typically would do in a targeted PFAS analysis, and it's also done after the sample is processed and it's oxidized in the laboratory. So by oxidizing the sample, basically the laboratory is subjecting the samples to some harsh conditions that will mimic the environmental conditions over a longer period of time and will accelerate the transformation of any poly PFAS into per PFAS. In theory, you would expect that most, if not all, of the poly PFAS in your sample to be basically transformed into per PFAS by the time that the test is done, the second test is done. So you have a sample, the lab tests it before it is transformed in the lab and after a laboratory procedures that will subject that sample to high pressure, high temperature, and so on, maybe alkaline environment and other conditions in order to transform those PFAS. And you analyze it again for targeted analysis. So you are using a very standardized and reliable technique, which is great. And now you are getting more information. If your sample has poly PFAS, then when you analyze the sample after laboratory transformation, you're going to see a distinct signature. You're going to see more of the per PFAS that you saw before, and maybe less of some of the poly PFAS that are targeted before in your sample. But now this is great. This is great. This is a lot of additional information that can help you, that can also help you show, oh, I have more PFAS in my sample, and maybe in the environment, I can expect additional regulated PFAS, per PFAS, forever PFAS to be produced in my environment in time. So you get you are more aware of the severity of your situation. It also can help in forensic investigation because it may show how your original fingerprint may change and how much is that subjected to change. But you are bound to the targeted PFAS. So again, you're missing all the other PFAS. So you are still limited to 40 PFAS or 80 PFAS before and after that oxidation. So it's a good step forward, but it's limited. And the other limitation of this particular technique would be that laboratory conditions may vary in between labs, no? And because it may vary, and some labs may generate higher degree of transformation than other labs, the final result may vary depending on the lab you are using. And we saw that in real data. But also, who's to say that the laboratory conditions would mimic exactly what will happen in the environment? No, I mean, the idea is, yes, these compounds will transform, but maybe in the environment they may transform to something else. Maybe the proportion will be different. Maybe it will never reach the proportion, the degree of transformation you see in the lab. It's hard to predict over how long, over time, this will happen in the environment. So there are all sorts of questions. So it's a big step forward, but we are still very limited. We still are dealing with limited information and potential confounding factors. So the third technique that maybe address some of these issues is a very general technique. It's not a new technique, but it's certainly new, more recently applied to PFAS and developed for PFAS. And this technique, it's called TOF, total organic fluoride. Basically, it's a technique. It's targeting the total fluorine in your sample that is linked to an organic compound. So if you have an organic compound in your samples that has fluorine, you're going to get the total amount of all these organic compounds as fluorine, reported as fluorine, and then it could be translated into PFAS. Now, this technique is great because you are not missing anything, no, but it has no specificity. So the other technique is extremely specific, but you are potentially missing a lot of PFAS. The total organic fluorine, it's non-specific. It will give you a number for that could be translated into total PFAS amount of your sample. Now you can be certain you are not missing anything, and you have an idea of how much of a problem you have at your site, and you know how much you need to treat, how much can generate the targeted PFAS. Because certainly when you do the targeted PFAS analysis and TOF, and you see a huge difference in total PFAS, and I think that could be order of magnitudes, like 1,000, 10,000, 100,000 times more
I'm
of
sure,
total
yeah.
organic fluoride, which is huge. Then you know you have a pretty severe problem. Versus if you do this analysis and you see a very small difference or no difference, then okay, yeah, then it's easy. So that's a great advantage of total organic fluorine. It gives you an idea of what the magnitude of the problem, but you don't know what you're dealing with. And I would say another important limitation is, let's go back to a definition. What is a PFAS? Now, the technique looks at everything, any organic compound with a carbon and fluorine will contribute to the result. But there are organic compounds, and those are a good example would be pharmaceuticals. And some of the pharmaceuticals are very common. I think Prozac is one of them. So, there are a few others, and I can provide a list or maybe a link where people can find more information. They have carbon and fluorine, and they are fluorinated organic compounds. So in a wastewater that has pharmaceutical waste, you're going to have those too. So, and who's to say, though, maybe half of your total organic fluorine or so on. Of course, it could be case by case. So we have to keep in mind, it's not only we don't know which exact PFAS are giving us these total PFAS concentrations, but also there could be non-PFAS compounds that will contribute to the total result and will exacerbate, if you like, the problem. But another, I haven't talked forensically speaking, TOF, it's also a useful technique. For example, I saw a paper where they look at AFFFs, different type of AFFFs, and they look at total organic fluorine in those AFFFs, and it was different in concentration. So at least originally, we have different total PFAS concentrations in different AFFF foams. And that could be an additional line of evidence, an additional fingerprint that maybe we can use when we have multiple AFFF sources. So it has forensic values. It certainly has values for evaluating the risk, maybe the toxicological risk and so on, even on a general or large scale, or the magnitude of risk, if you like, if not specific. And it really addressed the problem of, all the PFAS. It's probably more inclusive than it should be. And the last technique I want to point out, which is the most specific technique, and when I see the Eurofins webinars on this technique, it's really, I like the slides they are using when introducing this technique, and they show a very luxurious sports car, no? So maybe Toyota, Honda, this type of common cars would be the standard EPA methods that are looking at targeted PFAS compounds. And your Lamborghini would be this method, which is, of course, as Lamborghini is very expensive, but it will give you extremely useful data, particularly in forensic investigation, because this technique refers to non-targeted PFAS compounds. And those are PFAS compounds that we don't have a standard for, that are not tested by any other technique. And sometimes, or many times, we may not even know what is their structure. but we know they are there. And this is still a liquid chromatography technique as a standard analysis, but a standard analysis has a liquid chromatography linked to a mass spectrometry. This is linked to a particular mass spectrometer that is much more accurate. Time of flight, quadruple mass spectrometry, and that provides extremely accurate information without having standards. So just based on the chemical behavior, carbon and fluorine, it's supposed segments are supposed to behave a certain way and elute from your column at a certain time. And if you get those hits, which are not related to any of the standard PFAS, you still know you are dealing with a PFAS compound. And sometimes there are libraries, more inclusive libraries, that you can compare the structure and you can deduce what exact structure that compound has. And you have a CAS number and you have a name for that compound. Sometimes you may not be able to do that. But forensically, it's still important information because you compare sample between them and with sources or suspected sources. So that is an expensive technique. I wouldn't say it's less reliable, but it's less used. So potentially it may be challenged in the court of law more than the other techniques. But I think as an independent line of evidence, along with other techniques, it could be very useful rather than, just used by itself. And the last thing I want to point out is that regulators, regulatory agencies are more and more inclined to use these non-conventional PFAS techniques. And it's not just total organic fluorine, which is used, by many or is required to be used, but also the non-target analysis. And that's how, for example, I saw a paper, I can make it available, I think it was in New Jersey, at a location where there were two chemical manufacturers of PFAS. And I think it was Solvay and Chemours. They use this EPA used non-target analysis, and they did find a class of PFAS that was not known before and was associated to one of these sources and not with the other. And that's how they were able to distinguish what was coming from one source versus the other. Very interesting and clearly practical applications. And also in California, I think in some poor communities, small utilities, water utilities, they conduct a study using these two techniques, TOF and the non-target analysis, and they compare the data with the targeted analysis, and they found huge discrepancy. Targeted analysis was not able to capture more than half or even less of the PFAS that were out there. And based on that, I think California Water Board recently announced they secure funds to apply these non-conventional PFAS techniques to a larger amount of water utilities. So, I think it's coming, and not just in the forensic realm.
No, that's interesting. You gave lots of interesting information there, and I appreciate it. You kind of touched on the subjects about, the method challenges and overcoming analytical techniques. A couple of things I wanted to ask you about, and you could probably address them. And you just kind of even talked about there about different facilities that had a commingling of released materials. You talked about states, and you talked about EPA and federal methods, and you talked about intralab variability. How do you mesh all that together when states may be using ASTM methods versus federal that's using EPA, and then you have different labs that may have different internal, I'll say, SOPs or reporting limits or what have you? How are you able to more accurately or better kind of look at the data that is produced from these evaluations and help it to assist in either identification or differentiation and delineation for site contamination issues? How can you mesh all that together with so many, I'll say, other variable factors?
No, that's a good point. I would say specificity is a key.
Okay.
Specificity. When you're talking about PFAS, highly specific. There is not silver bullet. There is not one measure for all. Ideally, you would want the same lab to have handled and tested your samples across the years, no, in a forensic
Hmm.
investigation, ideally. However, I would not be much concerned with a standard EPA method. Now, before the method 1633 was available, like a couple of years ago, in order to analyze environmental samples, it was really like the Wild West out there, laboratories were using the drinking water technique 537.1 and just modify the technique. And that
Hmm.
was the only way to do it. I mean, it's not the laboratory's fault. I mean, that was the only way to handle the data and to report the data. There was no EPA standard method available. And in that situation, so if your data comes prior to 2021, I would say, or so, then you have to check the lab sheets, discuss with the lab the type of modification. If different labs analyze your sample at a site, in order to, when you want to compare the data, make sure you understand how the labs modified that technique when they when they analyze your sample. How did they handle the samples? And if you don't see any specific differences, then you should be good to go. If there are differences, then probably you need to consult a chemist and make sure those differences would not affect or bias the final result. So it's all case by case. The standard methods right now, I think, are pretty good. And the best way to do it is get a well-established commercial lab that that is certified. They could be certified by states, they could be EPA certified, and then you can't go wrong. I don't think so. So
Sure, and you kind of brought up a good point there of having the certified laboratory, and typically I have seen this a few times, and I'll get you to kind of give your thoughts on it too. In recent years there have been a lot of environmental labs. I see it from the exposure side and the environmental side that have been acquired by larger labs. They've become under the umbrella of other ones, and they have to operate differently. Have you seen any issues with the acquisition of any laboratories and transformation of what they were to now as compared to the data analysis or methods that they may have used back then to what they are currently using based on what is required by them by the overall new lab that they are?
yes, that's a good point. I personally cannot think of any particular
Okay.
example. I know that there is a trend in environmental industry and environmental commercial lab industry, to say so, to that large laboratories have acquired in recent years many smaller laboratories. I cannot think of a particular issue. I don't think it will be an issue. And even the same lab, I think it's possible over the years to change the way they modify a method. So just the fact that it's the same lab does not 100% assure that the same modifications were done or the exactly same procedures were done across the years. So it's always good to check, to double check.
And that's fair.
Yeah.
And one thing I like that you said, I'm going to ask you to just talk about this a little more, is, and I always talk about it in what I do, is, there is not a one size fits all scenario. It's going to be very specific for your scenario. I've seen a lot of people say, well, I've seen this and this is the way they're doing it here. I just might as well do it the same way. And can you kind of discuss the necessity of having an individualized assessment of the scenario or the site or contamination issue, because just because they seem similar on the surface doesn't mean underneath the surface they are going to be.
Yes. What you mentioned, it's absolutely right for any contaminants. That's ideally. You want to have a site-specific approach. But this is absolutely critical for PFAS. And the main reason would be because PFAS are unlike any other contaminants in the fact that we have all these polyfluorinated PFAS that will eventually transform into perfluorinated PFAS. So now you may be understanding your source, maybe, and you can look in the literature related to the source that you're having. Maybe it has been reported, it has been analyzed, you understand it. But every environment is different. And you need to make sure that whatever data you are using from the literature, for example, people are providing information on the transformation PFAS coming from various individual poly PFAS. And you can find that information. I had presented it in several of my presentations, and it's useful in general. But is it applicable for your site conditions? Because all these transformations are done in the lab. So keep an eye on that. Secondly, there is this cross-contamination issue. And I discuss in some of my past presentations, I'm still learning about it myself. And when we talk about cross-contamination, people think of sampling. Yes, there could be cross-contamination when you sample, but in general, it's not a big issue. And it is easily captured by using QC data and field blanks and equipment blanks and so on. However, when we are dealing with, for example, storage material, transport and storage, particularly storage for AFFFs, let's assume a company has used AFFF, legacy AFFF for a long time. And at some point they switched to modern AFFF. And they did not particularly change or clean their equipment and their storage. There could be enough left in the specific storage container, drum, whatever it is, tank, to contaminate the modern AFFF. And when the modern AFFF is spilled in the environment, it may retain the signature of a legacy AFFF. And if you're not carefully checking the exact source, get a sample from that tank that was spilled, then you may miss it. And it was reported, if you don't have time, maybe we do another podcast on this. It was reported in various locations. It may happen, and it may hugely influence the fingerprint you get. Another scenario would be you are clean, you have a modern AFFF that's spilled at an airport, and this happened in real life. And the regulatory, body requires you to clean to a certain level. You clean to a certain level, you check the PFAS that are regulated, carboxylates, sulfonates to a certain level. And that's fine, no? But if you don't check, for example, certain PFAS, it's because they are not regulated. Or maybe because you don't expect them to be in modern AFFF, such as sulfonates, they still may be there. And they may be there due to cross-contamination, or maybe it could be an older release that you are encountering in deeper soil. So there are extremely many confounding issues with PFAS. You have to be very specific. You have to understand, and even like talking to people who handle PFAS, to understand what happened. Try to get a sample that's representative for really what was spilled, rather than assume that what was spilled had a certain fingerprint or a certain composition, and take into account all the scenarios. And, I would end with my company, I'm right now consulting with Unsafe. And, we have a strong PFAS team that is looking at PFAS, but regardless of contaminants, I really like that my company always have this, I would say, T3 approach, like think things through. And I think it goes for any aspect of life, any aspect of environmental investigations, and it is critical for PFAS. Think things through, starting with sampling, analysis, and what you do with the data.
I think that's great. And I always tell people, individuals like yourself are the experts in this and what you're doing. And it's important to go out there and have you on the ground talking to people, understanding the scenario. Sometimes people say, well, do you really need to come out and do a site inspection? Can't we just tell you what's going on? And that is not helpful. That only gets me bits and pieces of the information. I'm going to be missing things. I think it's critical that people like yourself are able to go out and evaluate, and you said, think things through, know everything, identify it, especially if you're under some kind of regulatory review from EPA or otherwise. You're up against something where they have something that says you have to clean up to this level. You need to understand, is it rational to clean to this level? Is it physically feasible to clean to this level? It has to be all thought through. And I think you put it great the way you did. So based on kind of what we've discussed today, identifying the PFAS and the way to identify them in the environment, can you kind of give us a synopsis of what your thoughts overall are from the environmental contamination identification issue, and kind of also kind of discuss, what can people do to the prevalence of the material? What can people do to reduce their risk?
Yes, no, that's great. That's a good point. Well, I think first of all, PFAS are very different. We haven't seen them before. If something was working with other contaminants, so from an environmental perspective, it doesn't mean it will work with PFAS. They are so different from everything we have seen. If sampling is not a big deal with other contaminants, it could be a huge deal with PFAS. And again, that could be a subject by itself to discuss. How can you very well miss hotspots of PFAS just by sampling and not considering specific properties that PFAS have and that accumulation and interfaces and so on. That is very, very, very important with PFAS. Again, I said specificity. I would say the first time when we see compounds potentially regulated as a class and eliminated as a class, I would say these anthropogenic compounds, because they are not produced in nature, have background values such as metals. When we're dealing with heavy metals, we have to understand the background because they are everywhere and they come from rocks. As far as I know, there is not a general issue of background values for a chlorinated solvent or a petroleum product. No, so PFAS, when we're dealing with investigating PFAS, first of all, do not assume they are similar with everything else you have seen. So be prepared for the unexpected. Be very specific. Define the background of the environment, because right now they are in every environment. We have to understand what's the background, and you cannot clean below that background. It does not make sense. Also, the risk should be evaluated on a case-by-case basis, I think, and as toxicologists, you may know better. So be very, very specific. We see the trends. It's not like, oh, my PFAS, I saw companies that consider that their PFAS is okay. Maybe they have some studies, or maybe it's so different from everything we know that, it probably will never be analyzed for. No, will never. Well, there will always be, we see this approach that PFAS would be regulated as a class, and you may be responsible and litigated for having that PFAS that is so unusual that will never show up in any test except total organic fluoride. So as a company, never assume that because it's secret, nobody would know, and this PFAS is fine, it's different from everything else, it not be analyzed. Well, EPA can always come and analyze and find what it is, but also it could be regulated as a class. So that's what I see. I think stay away from PFAS from now on. For company, it's a big deal. It's not easy, but that's a message. And for environmental people, be specific, understand and learn every day. It's something that we keep learning, we keep being better, be open to things that may not be the way there are at other sites. Okay, I work at so many military sites, some people may say. I work at so many airports. I'm an expert, I know. Well, it might be different in this case because maybe you have another source on top of what you have, because maybe you don't have that petroleum associated, maybe you have a chlorinated solvent that comes there, maybe your site has been treated differently and the way it's treated for other contaminants may influence PFAS fate and transport. So it has to be very specific. Now, as a person that I suppose I have PFAS, I have to take measures for everyday person that want to try to reduce the exposure to PFAS. I think there are few obvious things that people can do. They are obvious to me. They are not obvious to everybody. So I would say first start with filtering your water. get a water filter. Even the can that you found at Walmart could be very good because they have these carbon filters. Maybe not the best, but you don't even have to install anything on your sink. Just get that water filter and filter your water. They are fast, they are cheap, and you never know. Maybe your water utility has not detected PFAS so far, but it might get detected a month from now or a year from now, and so on. So you want to be very cautious. Don't eat popcorn. Don't eat microwave popcorn. I used to eat. I love popcorn. I did not eat it too often, maybe once a week or so. I treated myself with a microwave popcorn, but I didn't know. Now I know. I stay away. So microwavable popcorn, they have PFAS in them. Obviously, that popcorn is subjected to the paper. They are in the paper. You cook them in a paper. It's subjected to high heat. So stay away from that. I would say get an air filter. That is always good for any type of contaminants. Some PFAS are volatile and they are in the air. Some are just in the air particles, in particulate matter. Having an air filter in your house, it's a very good way. Try to minimize, I would say, outdoor equipment. That's fine. You don't go outdoor every day unless if you go every day, try not to wear waterproof things. Get as little as possible. Don't wash them all the time, because that's a way that PFAS may go into environment. And particularly cosmetics, being a woman, we all like creams and cosmetics. Stay away from anything that's waterproof. No, we don't need waterproof mascara. We don't, everything may still have some PFAS in them, but the waterproof are almost guaranteed they will have PFAS. And, any common sense approach, and, try to inform yourself. For example, Google alerts are very good. If you put a Google alert on PFAS on your email, you may get useful information, what's new, what's out there. Apple News could be very good. Just keep informed. I learn every day. So I guess that's the main message. There could be many other small things, but for the most part, that's how you stay away from PFAS as much as you can.
Awesome. Thank you very much, Dr. Ioana Petrisor. Thank you so much for joining us today. We greatly appreciate your insight and expertise on this matter. So thank you.
Oh, I appreciate the invitation. I'm always happy to talk. And who knows, maybe we'll have some interesting news in the future. I'll keep you posted. I want to learn from toxicologists like you because it's all a matter of, a multidisciplinary approach. So.
Awesome. We'd love to have you back. Thank you so much.
All right. Well, thank you.